All right, let's talk a little bit about the carbon cycle. I'm not going to talk too much about cellular respiration and photosynthesis because really this part should be super familiar for you guys. We know that in photosynthesis, plants like to take up CO2. They store it in a way. If we're looking at just removing CO2 from the atmosphere, they're storing the carbon as C6H12O6, which is glucose. And that carbon can get used during cellular respiration. Of course, getting burned with oxygen by the mitochondria in any cell that needs energy, which is all of them. And then cell resp is going to spit out CO2 again, as well as water. So that part of the carbon cycle you should be familiar with, and it is quite a simple part. I think most of you guys are also familiar with burning fossil fuels because they're made of carbon. That's going to produce CO2. Deforestation, if you cut down forests, we have less of this photosynthesis part, and so even dead cut down trees are going to be using up some of the oxygen and some of the glucose that they store, and they're going to produce more CO2 as well. So overall, deforestation can definitely increase that level of CO2 in our atmosphere. So we're going to leave those concepts. Same with volcanoes. That kind of makes sense. If you're spewing hot magma, there's going to be some CO2 that's produced as well. We're going to focus on just the ocean part. The ocean, because it covers about 70% of the Earth's surface, it of course is going to play a big factor in this cycle. So I'd really encourage you guys again to draw this along with me. I know some of you guys might not love that, but drawing is such a good tool for learning. And so especially with the cycles that it's a bit harder to pay attention to, they're kind of boring. If you draw them out, I think you'll find that you remember more of them. Okay, so we're going to draw some CO2 as a gas just floating around in the atmosphere here. Something I'd like to just kind of comment on. If you heard reported in the media today that, oh no, CO2 levels have risen to 2% of our atmosphere, you might think, 2%, that's nothing, that's not a big deal. But if we know that CO2 at its regular concentration in our atmosphere should be 0.03%, that's all that we need to do the natural greenhouse effect, basically what we need in our atmosphere to keep us from freezing our butts off and keeps a little bit of the solar radiation trapped and bouncing around in our atmosphere. That's a really tiny number, and that contributes quite a bit to us having a warm and stable temperature on Earth. If the CO2 concentration went up to 2%, that would be catastrophic. That would be ridiculously a big deal. Okay, so I just thought that was something important to point out so that if you're looking at articles in the media and trying to figure out what to think of them, it's important to look at the scientific facts of what is actually normal, and then you can decide for yourself if those changes are a big deal or not. All right, so we have CO2 hanging out in the atmosphere. In the ocean, we actually do have a little bit of photosynthesis and cell resp, that part of the carbon cycle going on. The ocean actually has cyanobacteria, which you guys might have already read about, making up those mats, and cyanobacteria were one of the first producers. Cyanobacteria, as well as, these are sometimes called blue-gray algae. We also have something called phytoplankton, which are, again, microscopic little photosynthesizers. So your cyanobacteria and your phytoplankton, they actually produce most of the oxygen in our atmosphere. So those are really, really important to take up some CO2 in photosynthesis and to produce oxygen. Okay, so that's a really important part of the cycle. Now, of course, they're not going to be able to do that with all of the carbon that's in the atmosphere. Some of the carbon, it just naturally gets mixed in with the water. And that helps to keep our atmospheric concentration stable to a point, okay? So some of you guys might have heard how CO2 in the oceans, it can cause the oceans to become acidic. And maybe you're wondering how that happens. This is going to kind of solve that for you. So when we have CO2 now in the ocean, what compound do you think it's going to encounter a lot of? Water, H2O. Okay, and if you guys remember when we were learning about the respiratory system and how CO2 travels in the blood, water and CO2 undergo a reaction where basically we take all of the hydrogen, so H2, all of the carbon, and all of the oxygen, so 3 total oxygens, and we make H2CO3, aqueous, because it's dissolved in water, and this is also called bicarbonate. So H2CO3, again, you might remember this, learning this earlier, or if you're good at chemistry, you might have looked at this. H2CO3 is an acid, and so acids, they like to produce hydrogen ion, and that's what actually makes them an acid. Okay, so this dissociates, we get hydrogen ion, we get CO3 minus. Oh, sorry, this term came in too early. My apologies. Relating to this being an acid, geez. This is actually carbonic acid. And we also call it hydrogen bicarbonate. That's where that carbonate part came from. If we remove the hydrogen, we just call this bicarbonate ion. Okay, so hopefully this is giving you guys a little bit of a picture of why we have our oceans becoming more acidic. And this can be a problem for coral reefs as well as any aquatic life that's living there. Most things like to have a pretty stable pH. Most things do not like to swim around in acid. It's not good for them. So that's where that part comes into play. One of the main reasons we don't want to have too much CO2 going into the ocean. Okay, so now this bicarbonate ion, 2 minus, geez, me and my little mistakes all over the place. Okay, this bicarbonate ion is now going to go through another reaction, okay? And so some of this bicarbonate ion just stays as is, floating around in the ocean. Some of it combines with calcium and forms calcium carbonate. Bicarbonate. And so calcium bicarbonate, it actually becomes a part of the bone, or not the bony structures, the shells and some of the other structures in aquatic life. Okay, so things like snail shells have calcium bicarbonate. Same with the skeletons of, or the exoskeletons of things like lobsters and crabs have some calcium bicarbonate in them. Okay, and so that gets stored in some of the shells of aquatic creatures, as well as in some of the sediment, which is basically teeny tiny rocks that are floating around in the water. Okay, so this snail is going to live a long, healthy life, but eventually he might get eaten, his shell gets crushed up, or he just dies of natural causes. So that shell eventually can get crushed up, same with the shells of all sorts of other aquatic organisms. When they get crunched up, they join the sediment, and all of that calcium bicarbonate can get packed down into rock at the bottom of the ocean floor. Okay, and so that whole process is called sedimentation. Okay, and it's going to become compacted over lots and lots of time. When you guys were looking at that graph and you were trying to answer those questions from the textbook, you saw that carbon dioxide has a very long time that it can spend in the ocean and stay trapped here. So part of that reason is if some of that carbon is becoming a part of calcium bicarbonate, it's going to become a part of the life cycle of these organisms, and then it gets packed down into rock. And rock can stay around for a really long time. Okay, so aside from the acid part, That's obviously bad for aquatic life, but you might be thinking this seems like a really good way to just get rid of some of that carbon that's in the atmosphere, okay? Because it's just going to stay trapped in the rock at the bottom of the ocean now. Unfortunately, there is a final step where that does not always stay packed in the rock there. Okay, so the rock at the bottom of the ocean is actually called limestone. And limestone, of course, because it contains all these packed down aquatic creatures and their shells, it is primarily made of calcium bicarbonate. Okay, so this limestone just sits here, but over geological time, over a long period of time, we can have a process called geological uplift. It's a natural process where as the plates are shifting, rocks are moving around, some of them that were on the bottom get pushed up towards the surface. Okay, so we got this limestone here now. Limestone can also be pulled up to the surface by mining because it looks really pretty. It's kind of white and sparkly, and is sometimes used for landscaping and building structures, building statues. It's a really nice looking stone. So here is where this becomes a cycle. We can't just have things going one direction in this cycle. This calcium carbonate does not necessarily get to keep that carbon once it's at the surface. If it encounters acid rain actually causes another chemical reaction that releases that CO2 from the calcium carbonate. Okay, so acid rain, you guys might have already learned this in your reading. Acid rain, it's formed from nitrous oxides as well as sulfur oxides primarily. Both of those can be released into the atmosphere through burning fossil fuels, especially coal is really, it doesn't burn very clean and produces more of those. When these dissolve in water, they form nitrous acid and sulfuric acid. Not so good. Okay, when those get dropped onto limestone, we have a similar reaction to here, where an acid is releasing carbon, okay, but slightly different. So we actually end up with the CO2 getting released back into the atmosphere, and the other parts of limestone stay trapped in the stone. So not only does that degrade the stone, it's not going to last long term on the surface, but it's also releasing that carbon dioxide back into the atmosphere where, you know, it might get sucked back into the ocean and go through that long cycle again.